All right, welcome back. Now that we've looked at gradients in detail, we can talk about our first and very basic but very fundamental algorithm called gradient descent. So gradient descent applies to what you would call an unconstrained optimization problem. So you have a scalar valued function f, like we've been dealing with up to now, and we want to find its minimum. Say we want to find the w that minimizes f, or in mathematical terminology, it is the argmin of f of w. In optimization lingo, f of w is called the objective function, which usually for machine learning problems will be the loss function. And w were sometimes called the decision variables, but these in machine learning would typically be the parameters of your model. This is called an unconstrained problem because, at least the way it's formulated here, you're allowed to pick any w you want. We will talk about constrained optimizations briefly in the next unit, but they require us to develop a little bit more math. So for this unit, we'll just be talking about the unconstrained case. Okay, now, how do you find a minimum? Remember, what we just learned was that at least at any local minima, the gradient is always zero. The gradient being zero could happen also at a maxima or a saddle point, but you do know that if it's a smooth function, the gradient will be zero at any local minima. So usually you try to solve those equations, and if you have m variables in w, you'll have m equations and m unknowns. And this is what we did, for example, in least squares. You can analytically find the closed form solution. But generally you don't have this, so you have to do what we would call a numerical method. And that's what I'm going to show you one such method now. And a numerical method basically tries to get a sequence of w's that hopefully converges to some good local minima, which I'll talk about that momentarily. And typically this is run on a computer program, and I'm going to show you how to code one of these numerical methods up. All right, with that in mind, I'm going to show you the very, very simplest method, which is just gradient descent. And this only works, as I said, the way I'm going to write it for unconstrained optimization. There are variants for constrained ones. So there's one thing to remember from the previous section, is that if you can compute the gradient of your function, the negative of that gradient points in the direction of steepest decrease. So imagine your function's like you're sitting the altitude, so you can think about where you are at some point, and if you wanted to go down in altitude, like down a hill, that gradient would be pointing in that direction. All right, so this is the gradient descent algorithm. It's super simple. You start at some initial value, which may not be very good, and then the next value in each update, I just take a small step in the direction of the gradient, or the negative of the gradient. In other words, hoping to go lower. And I just keep on repeating this loop until some stopping criteria. This alpha k is called the step size because it tells you how much I change from one step to the other. And in machine learning, it's called the learning rate. I'm going to give you lots of programming examples of this in a moment, but let's just try to visualize what actually happens. First, let's take a look at the case of one variable. In this case, the gradient is just the derivative. So say you started this way. The derivative in this case is negative. And so if the negative of the derivative would be positive, so it would tell you to move in the positive direction. And you can see here that that is indeed telling you to go down in value of this function. So you take some step. At the next step, it would also be negative. It also tell you to go in the positive direction. So you take another step, and so on until you eventually converge. You converge because as you get closer to this bottom of this valley, the gradient goes to zero. So you start slowing down the amount you're moving. Here's a 2D version of this. Imagine this is the bottom of a valley in some contour plot. I start like this. In 2 dimensions, the gradient is always pointing on the tangent of that curve. So it points you this way. You can see it's sort of pointing you in this case to this minimum here. So you take a jump, and then you take another jump, and so on, and again you will eventually get to this point. So that's kind of the picture proof of that. If you want a more mathematical proof, I don't expect this is too much, that's fine. I'm just putting it here if you want the mathematical details. If you want to prove, though, that it will always decrease, this is the basic logic. I look at the value of the function on iteration k plus 1, and I want to compare it to the value at k. Well, I can use my first order approximation. I know it will be the gradient, the inner product of the gradient with the difference of the 2 values plus some second order term. All right, but we know that the difference of values is just going to be alpha times the gradient, and this is none other than the gradient, norm of the gradient squared, times here the step size. And this part here will kind of decrease by order of alpha squared. So if you look at this, if I make alpha very small, I can neglect this term, and you can see that f of w of k plus 1 will be lower than f of w k with this term here, which is proportional to the step size, since this one's always positive. So it'll always be decreasing, and that's, okay, kind of a little bit more rigorous proof. The point then, so that if the alpha's step size is sufficiently small, the function will always be decreasing. And you can prove this a little bit more formally and show that if the second derivative is bounded, and well, some technical conditions, the gradient will indeed always converge to a local minima. Now, I've been using this term local minima a little bit, so I want to just point this out because this is very important for optimization. Let's take a function like this. This function is said to have 2 local minimas. There's a minima here, but there's also a minimum here. Local minima just means that you're a minima within the neighborhood of that point. So if you were here and you only saw the local points around it, the points that are close by, this would be the lowest among those points. But there is another local point way over here. This point, though, is actually called the global minima because it is the lowest value amongst all points. Now, here's the problem with gradient descent. Gradient descent only guarantees that you converge to a local minima. So, for example, if you start here, gradient descent will decrease and land at this global minima, which is great. But if you start here, gradient descent will push you this way, and so on, and you'll get stuck here. And it will locally look good, but it will never find this other point. And this is a general problem with gradient descent. Now, it turns out that there are functions called convex functions that only have global minima. That is, there are no local minima that are not global. So this problem can't occur. I'm not going to post a video about it, but you can check it out in the notes below and read a little bit more about this, and it's certainly covered in any optimization class. But this is just an important concept to keep in mind. All right, we're almost ready to go with this to start coding up gradient descent for our logistic regression problem. We just need, the one thing is to compute the gradients of logistic regression. So let's recall how logistic regression works. We have our data X matrix, and we have some weights and bias. And what we do is we first compute a linear function, which we'll call Zi. And then if you recall, we compute some output probability in the binary case, the probability that's in class 1, some logistic function of Zi. So this function is from 0 to 1. And then we want to compute this binary cross entropy, which I've shown here. And we reviewed all of this in the previous unit. Just want to talk now about how to minimize that function. So we need to compute the gradients to be able to implement gradient descent. And all we do is fairly straightforward. It's actually pretty much exactly what we did in the other example in the previous section. We first define a matrix A, like we always do, which has ones in the first column, right? And then we can write our Z's just with the A's. So it's just the A's times the W's. After we get this, let's just call this probability Pi, just for the sake of notation. So this is the probability that the ith sample is 1, or what our model says. And now, when you want to take the derivative of j with respect to zi, you just take the derivative of this, which will be the derivative of this term, minus the derivative of this term, and this with a little bit of algebra, you can show as pi minus yi. And once you've got this, we can compute our derivative with respect to wj with the multivariable chain rule. So we take the derivative with respect to each zi and each zi with respect to wj. And we've computed both of those up there, and we are done. So now, at least in formulas, we can compute the gradient. But when we want to implement it in Python, we want to do it in a little bit more efficient way. And the best way to do that is through writing it in matrix form. And that's also fairly easy. Here are the equations. I just wrote them above. If you want to implement this in matrix form, all you do is you just step them through one at a time. That first equation, you could just write as the vector z is a times w. The next one is just going to be p, that p matrix. It's 1 over 1 plus e to the minus zi. And then dj dz is just going to be this p minus y as a vector. And then this one here is none other than a transpose times this. So you have 5 simple matrix or vector equations, and you can easily implement that in Python. So if I wanted to write my function to evaluate the gradients, it takes the parameters w, and it takes the data matrix x and the labels y, constructs the A matrix, that 1's in the first column. I'm going to compute z is equal to a times w, then I'm going to compute this vector 1 over 1 plus e to the minus z. I'm going to evaluate the function like this, and then I'm going to compute the gradient, which is p minus y, and then I'm going to compute that gradient, which is a transpose times that. Okay, so now we're done. We're going to dive in to actually coding up the gradient descent for this logistic regression problem in the Jupyter Notebook. All right, now I'm going to show you how to code up really what would be a bare bones gradient descent optimizer in Python. As usual, I've created a notebook and in the GitHub site. You can run that again on your local machine if you've downloaded the GitHub site to your local machine, but I'll just run it on colab.research.google.com as usual. So once you go there, you'll get this dialog box. Click on GitHub, enter the GitHub site, which is https://github.com/sdrangan. After you do that, select the repository for this class, intro OML. Scroll down to unit 7, and it's the second demo. The first demo is the one that I was giving the examples for the gradient computations. So that's on gradient descent. After you click on that, the demo will open up. The first thing we're going to do is just open some or load some standard packages. Remember, it will ask you on the first time for permission. Now we're just going to load the breast cancer data just as a test data point. Since we already did this in the previous unit, I'll just run these cells. Remember, it grabs it from this data set, from the UCI data set. It drops the missing values and displays our data. So remember, in our data we have 9 attributes for each sample, and we want to determine its class, whether it's benign or malignant. That's this class here. So we're just going to grab a data matrix X and a vector of target values Y. We remember we had to convert that number class of 2 or 4 to 0 or 1. That's all this syntax is doing. All right. Before we actually try to fit the logistic regression, what we want to do is, again, some pretty standard steps. We want to split the data into training and test, and then do the scaling of the data just as before. So I won't review this because all of this is explained. Now, the results you get if you run this notebook will depend on the particular train test split. That is why in the unit 6, where I did this, I did the k-fold validation. But I just want to illustrate the optimizer here. And I want to just get a reference point of what sklearn's built-in optimizer does on this particular train test split. So it's super easy in sklearn because they've built this whole optimizer, and a much better optimizer than what I'm going to write here. It's all built in. So it's easy. All you do, if you recall, is you create a logistic regression object, and then you fit it on the scaled training data, and then measure the samples on the scaled test data, and you can look at the accuracy. In this particular case, I got about 95.6, almost 96% accuracy. For different train test splits, it can be quite different. Sometimes it could be as high as like 96, 97. It just depends on the particular split. All right. So the first thing we have to do now to write our home-built, home-crafted gradient descent optimizer is writing the actual function to compute the gradients. This is actually the only hard part, to be honest. And we already covered that. And if you recall, this is the code to do that here. So we have a function. It takes parameters and the data values x and y. It computes the linear discriminants z, computes the probabilities, the loss function, and then it computes the gradient. And we've just gone over this, so I'll just run this so this code is sitting there. Now, before we can actually do the optimizer, there's one slight issue. This function evaluation method takes 3 parameters. It takes the vector of weights, w, that I'm trying to fit, but it also takes these other parameters, x and y, that are actually constant during the optimizer. When you try to use a generic optimizer, there's no obvious way to pass in these variables x and y, because the optimizer is only concerned with this vector w. So you have to rewrite another kind of wrapper function that removes this x and y. And I'm going to give you 2 quick methods. One method is a little more complicated, but I think it's the kind of preferred way from an object-oriented perspective. And this is what I tend to do. You don't have to do it, though, this way. I would create a logistic function class, and in the constructor for that class, I would pass it x and y and save them as member variables. And then I'd also do any pre-computations that need to be done before every time the function evaluation is called, so they don't have to be repeated. So that's what I'm going to do, and I'm going to store also that transform matrix A with the 1s. Now, every time the evaluation function is called, I only need to give it the new data w, and I can call up this matrix because it was already stored here as a member variable here, like this. And then I can run basically the same computations. And so now I have this logistic function class. If I want to use it, all I do is I create an instance of this class with the training data. Remember, this is the scale training data here. And then I can always call that method feval within that function to evaluate at a particular weight w. So that is all what is happening here. I'm just giving it some random weights, and then I could call it here this logistic function class object with this member function feval. So now you can see I'm no longer passing x or y. So that's a little bit more mechanics, but it's maybe preferable from the standpoint of having an object-oriented perspective. A simpler way, if you prefer, is well, you can just do what's called a lambda function. So I have this other function here, feval, which takes w, x, and y. I'm going to create a new function called feval of param, and it takes w, and it just adds in the training variables and calls this. So that's a much simpler way to do this. Either way is fine. It's just how you like to organize the code. And now you can pass it a parameter w0, just like this, whichever you want. Okay, one last step before we actually code up gradient descent. Remember what I told you in the previous section. Always, always, always test your gradients to make sure you're doing them right. It is the number one error that people get when their gradient descent doesn't work if you're writing with hand-coded gradients. So the way we did that, remember, is we take some initial value, and I just take it random, and then I take another value that's close to the initial value. I evaluate the gradient and the function at the two values, and I make sure that the change in the function is close to the estimated change that I would get based on a first order model. So always do this. Okay, if we do this here, I get they pretty much match. I think if I went out more decimal places, there'd be a slight discrepancy, but you can see here that they very well match. So that's good that we know that it's, at least for this one data point, it's working. All of this work is actually the hardest part. Once you have done all of this, gradient descent itself is super easy to write. Here's a super bare bones gradient descent optimizer. It's literally, 5 lines of code. You pass in a function. Now that might just be the only conceptually difficult thing to understand, because we're used to passing numbers or arrays. We're actually passing in a function as one of the arguments for this optimizer. So here it's called grad op simple, and it takes a function and some initial value, a learning rate, and a number of iterations. And then all it does is this. It initializes the w, and in each iteration, it gets the function and gradient and updates, takes the gradient step. It updates that w by a small shift in the gradient. And after you run it enough iterations, it gives you the function and the final w. And that's it. Literally, 5 lines of code. Just for the purpose that we can understand a little bit more of how it behaves, I've written a slightly more elaborate version. Actually, it does exactly the same with the w, but I just put in this history dictionary. So all this does is that on each iteration, it records the function value, and it also records where it was in w. And I'm just doing that so we can just record what's happening, just to see how this works or doesn't work. So, but it's basically the same 5-line algorithm. And now we're actually ready to test this out. So let me just load this function. And here we go. I'm just going to start it with a completely random initial condition. I'm going to put the learning rate to some value, run it for 1,000 iterations. The function I'm going to use is my function that I created up there. And I'm going to call this simple estimator. And I'm going to plot the value of the loss function as a function of the iteration. So this is the loss function on the y-axis. And maybe I should label that so you can see. That is the training loss. and I'm going to label the x-axis here as iteration. Okay, a little bit nicer to view. And you can see that it is starting at some value, and then it goes down and down and down and down and down, just as you would expect gradient descent to do. Now, we're not actually interested in the loss function itself. From a machine learning perspective, that's just a means to an end. What we want to get is generalization error. So we want to see how well this does on test data. So I'm just going to write this hand-coded predict function, which will take my W and take an X data matrix and predict the labels by finding the linear values, and then testing if the linear values are positive or not. I'll run this on the test data and measure the accuracy. In this case, I get 94.1%. You can see it's quite a bit worse than what I was getting with sklearn's optimizer, which was about 95.5, 90, something like that. That is, the reason is, if you look at this very carefully, you'll see it is going down, but it still has ways to go down further. It didn't really level off. So we could run it for more iterations, or we could try a faster learning rate. That is all I'm doing here. Try actually 3 different learning rates. A really slow one, about what we tried before, and about 10 times faster than this. And for each one, I do the same experiment and plot the results. And I'm also going to measure the test accuracy. So let's just run that. This optimizer is pretty fast. And you can see here that if I pick the faster learning rate, it's getting pretty close to what the sklearn optimizer did in terms of test accuracy at the end. If I ran it for a few more iterations, I would actually be able to get it, or you actually could probably speed up the learning rate a little bit more and actually hit it. Also plotted are the training loss as a function of the iteration. So here's the iteration, here's the training loss, and you do see indeed that in all cases it's going down, but you see that when you have a higher learning rate, it goes down much faster. Now that might compel you to think that you should just pick the learning rate as fast as possible. The problem is if you pick it too fast, it can go unstable. I haven't picked any learning rate like that, but go ahead, run this with even higher and higher learning rates. At some point, you'll see it will actually diverge. So you have to be a little careful. That raises another issue, which is how to pick this learning rate automatically. So in the notes and more in this notebook, I talk about one method to do this using the Armijo rule. I'm not going to go over this, but in this YouTube lecture, but check it out if you want to dive a bit more into this. And in general, optimization is a huge field. So if you get a chance to take the class, you'll cover this and all sorts of other techniques to make your own optimizers much, much better. This was really the most basic version I could give you. What I want you to try to do, though, is just scroll down to the in-class exercise at the bottom. This is really just actually optimizing a scalar valued function, but it has a local minima in it, and you can see what the optimizer does. And after you get through this, you should be ready to go on to the lab where you'll do your own handcrafted optimizer on a non-linear regression problem.